Okay. Well, you find different types of modules in a modular synthesizer. Like you have oscillators, you have filters, you have modulators like envelope generators and LFOs, and you will also in almost any synthesizer find a noise generator. And noise generators, the sound of a noise generator is this. So for many old synthesizers and new synthesizers, there is something that one module that says noise, and mostly it has only one knob or no knob at all, and if you listen to it, then all the time that hiss. So I thought, well, noise is in itself a very interesting kind of sound of wave phenomena, because basically in noise you find every pitch, it's a sum of an enormous amount of partials, of sine waves, of every pitch at every level and continuously changing. So basically it is sort of like everything is in there. So you can sort of compare it to white light, sunlight, white light. It contains every color, because if you take a prism you can extract red or green or blue from the white sunlight. So now this is, so basically every possible sound is hidden somewhere in noise. And but that is a theory. This is already an old idea, and in the early 60s there was a Dutch composer, Jan Boerman, and I'm very grateful because today I got a beautiful present, and that is a record from Jan Boerman. Especially this piece, the Zee, is very nice. So really, thank you very much. Because Jan Boerman, he was very much aware of this idea, and he said, well, if you have a sound, you can classify it between somewhere between the most simple sound there is, which is a sine wave at a certain pitch, and the most complex sound that basically contains every sound, and that is noise. So in his composing, he used sounds that were filtered from noise. And so because within noise there are certain things. So I thought, well, if you build a noise generator, then it would be nice to sort of be able to create sounds that are somewhere in between noise and something very simple. So the thing that I did was I just made basically a simple sound. Which is, as you can see, a little bit like a sine wave. But then, what you can do is you can modulate this sine wave. Or you can modulate both. enter these territories between a sine wave and a noisy wave. So the trick that is used for this is that you use to create the noise, you use what's called a pseudo-random generator. The sound of the pseudo-random generator is basically the noise sound. And this so-called pseudo-random noise is generated by what they call a shift register, which is just a chip, and it's a digital function that is used in many devices because it is a device that is able to transform so-called parallel data into serial data, and serial data back into parallel data. And old computers, they had printers which had a so-called parallel port, which means that they had like 10 wires connected to the computer, and the combination of zeros and ones on the 10 wires would define what the printer would do. But then they came with the so-called serial interfaces, and that basically had only 2 or 3 wires, and one wire would sort of sequentially get the bits on and off. And these days we have USB, Universal Serial Bus, which means it is a serial protocol, and so a shift register is used somewhere to make parallel bits into the stream of serial bits. Networks are serial information, so to be able to transform parallel to serial, serial to parallel, you use shift registers. So they're really common chips. But the interesting thing about a shift register is basically it's sort of like an array of sample and holds. For instance, if you would have 8 sample and holds where the output of each sample and hold is connected to the input of the next one, and that one, the output is connected to the one after that, and they all share the same clock. You can imagine that if they are perfect sample and holds, that on the first clock pulse, some outside signal is sampled into the first sample and hold. Then on the next clock pulse, that value will be clocked in the next sample and hold, but the first sample and hold will actually get a new input value. And that will sort of fall through the pipe of sample and holds. Now the shift register is basically such a device, only it can only sample zeros or ones. But the interesting thing is that we actually have waveforms in the synthesizer that only are made of zeros and ones, and because those are square waves and pulse waves. Because with a square wave or a pulse wave, it's either a high voltage or it's low voltage. So you can consider that as a digital wave. So you can directly connect such a shift register to square waves. So the idea is that you have a clock for all to shift all the samples through the pipe, and you have an input where some outside signal, 0 or 1, comes in. So if you have 2 square wave oscillators and one of these shift registers, you can use one of the square wave oscillators to clock, and the other would provide a 0 or a 1 on the data input. And then you get an interesting situation, because on many of these chips that have one serial input and then lots of the parallel outputs, then you will create a bit pattern on the outputs, and this bit pattern can be interpreted as a digital value, 4 bits or 8 bits or 3 bits. And then you can use the so-called digital to analog converter to create an analog voltage that is basically the same as that code. So, and what is also interesting is that basically this is also sort of kind of digital delay. But the most simple, worst quality digital delay there is, it's a 1-bit digital delay, not 24 bits, no, it's only 1 bit. If you would use 24 in parallel, you could actually process 24 bits, but now but because it takes time before an input comes to the final output. So you can be very creative with this idea. So I think this already goes back to 1980 or something, when I remember very well when it happened, because it must have been like 1980, 1981, because I was much younger and I like to build these plastic model kits and paint them and do things with them, and I had this really nice model kit of the Apollo lunar lander, and I really painted it nicely, and I wanted to hang it from the ceiling, but I thought, this thing must have sound. Constantly there must be some sound coming from the thing. And in those days there was this this shop, the Tandy shop. I think later they became Radio Shack, I think, I don't know. But in those days you actually had the Tandy shop, and the Tandy shop they sold chips. And a limited assortment of chips, but some of them were quite interesting, and one of them was called the SN76477, if I remember one, and that was described as a complex sound generator. So big chip, 40 pins, and you got a nice paper with it that said what it would do, and it was basically developed to make sounds for the old Pong games and the old arcade games, and sort of like, so you could sort of program it to make a gunshot or a siren and things like that. But the architecture of the chip was interesting because it had two oscillators, two voltage controlled oscillators that would give either pulse waves or triangle waves. And it had a noise generator, a pseudo random noise generator, and a VCA and a sort of very rudimentary envelope generator. And I was just thinking like, I must make something with this and put it in the model, but I want to have this sort of space sound, sort of bleeping signals from spaceships to spaceships, and not just a siren or something. So I was sort of thinking to make a little sequencer for it, and I was experimenting with it, and at a certain moment I remember I just connected one of these shift register chips on the which I thought if I put that on the noise output, then I can get a random step signal. If I feed that random step signal into the oscillator voltage controlled inputs, then it must play little sequences. And I just accidentally connect the data input to the second oscillator instead of the noise generator, and then suddenly it became much more interesting. So and basically that, so because I was basically clocking it from one of the two oscillators, and then it would get the data input from the noise generator, and that would produce a step voltage, and that step voltage was fed back into the second oscillator. But because I accidentally connected the input of the shift register to the output of the second oscillator instead of the noise generator, it suddenly got the clock from the data from the second one, but that was also modulated by this voltage, and something really interesting happened, because it sort of produced, because random noise produces a pattern which never repeats, or only repeats every so many hours or something. and it just wanders aimlessly. There's no structure in it. But this suddenly produced a structure, because it seemed to produce sequences that were sometimes maybe 4 steps, and sometimes there were 20 steps, and it sort of actually I didn't realize it at the time, but it created basically a chaotic system with all the behavior of what is described in chaos theory. So that thing sort of kept in my mind, and then when I wanted to make it a noise generator, I basically thought, well, I need to use this principle, because actually you can use this shift register to create pseudo-random noise, but if you just manipulate it in another way, then you can create this sort of patterns which are in between total chaos, total randomness, and sort of a pattern. So basically, what you can do is you can first of all change the noise clock, which creates sort of like a phasing kind of sound. And then if you go really low, then you see that you actually get step voltages. I can show that on the scope, of course. So you see you have several levels, but it's just without structure. But now I have a switch, and now I can actually sort of hold the pattern. And I can also already hear that some interesting things are happening in the noise. Okay. Now it becomes interesting to start to filter this noise. That point, it can be actually interesting to sort of also modulate the filter with the same signal or a related signal. Then feed it back into the oscillators. See that I did a quite extreme transformation, because if I stop the filter modulation, fully open the filter and stop with the modulations here, back to audio rate, then finally come back to my noise again, without repatching cables, just only this Wrangler and the twin peak filter. So one of the ideas behind the Wrangler, so basically the Wrangler is a noise generator. That's why you start with noise. Well, I started with noise, but then you can go into completely different territories, and you don't really need a lot more. Maybe only just a filter or something to create things that have sort of a structure, but a more or less random structure. You don't really know where that structure comes from. It's you can influence it, but you cannot. It's like a chaotic system. Basically, a chaotic system means that it is a very ordered system. But the order is so complex that our human mind is not able to grasp it in its full complexity. So to us it appears like randomness or noise, but of course there is a very fast computer can calculate it, or a Wrangler can produce it. And I like Wranglers because they produce it. So basically, while most noise generators don't go much further than sort of like going from white noise to pink noise to brown noise to a randomly fluctuating voltage, you can do more interesting things here. By starting to add modulation. Like now I really slowed down the noise sound, so it gets a completely different kind of structure. That I like to do with filters is I like to build filters in a way that you can modulate them with audio, not just only with LFOs or envelope generators, because it's called filter FM, because I very much like filter FM, because if you want to change the character of a filter, then if you add a little bit of filter modulation, FM, filter FM, you get a completely different kind of filter. Actually, I use a clever trick, because I use the VCA output of an oscillator. If the signal comes out. So I can actually put it in the 1-volt octave input of the filter to have an extra filter input. Then I can open this and here that you get quite extreme. And the nice thing is that this is now also immediately modulatable, because if I use the VCA input, I can connect it to, let's say, the triangle wave here, and maybe an envelope generator. I'm not using a lot of modules, and you already get some. I can actually also listen to the VCA, because then the VCA are interesting things just to play with and to explore and just to find out if you can come to a particular kind of thing that does something interesting. But the trick is mostly, well, sometimes you can start with something that goes normally goes slow, and then you speed it up extremely, or you can do something that is normally quite fast, like at the audio rate, and you really slow it down. And that's the nice thing about the Wrangler, because the Wrangler, let's just destroy this patch for a moment. The thing about the Wrangler is that basically, if you feed it back into itself, then you start to slow it down in time, but in a random way, sort of like a random way. So, which is this. And then you can use these sort of blocks to create pings, and you hear that sometimes it's really slowed down quite extremely, but sometimes it's relatively fast. Now it's stuck in a pattern, but if I slow down this pattern, okay. Does this make sense? Okay. Shall we have a little break? Maybe I brought sandwiches and food and lunch, and maybe have a short lunch break.